Hello, welcome to this course on modeling analysis and estimation of three-phase unbalanced power network. We have been talking about transposition of the lines and we also have looked into the calculation of sequence impedances. Now we will carry on. So today first we will talk about the case of fully transposed line. So today we will first talk about completely transposed line. It is also called fully transposed line, that is also the name. Basically the completely transposed line or fully transposed line basically is S1 S2 is equal to S3 is equal to 1 by 3 into S. So essentially these three distances, we have said that if I have essentially what we have talked, that if I have three lines, this is position 1 2 3 and this is A B C, then we said that then so this is the case we have talked about. So this is A, then B, this is C, and then this is B, this is B, and this is C. And the distances are, that this distance is S1, this distance is S2. That is the concept of the transposition, and let's say that this distance is S3 and the total distance is S. Total distance is S. So that is the case. So in the case now, basically so far what we have considered that S1, S2 and S3 can have any value, they actually need not be equal to each other, but then of course they will have to obey the relation that S1 plus S2 plus S3 is equal to S. That relation must be always satisfied, but then they really need not be equal to each other. So when we are talking about completely transposed line, we are talking about a very special case where all these three sections of are equal length. Now we would like to see that what happens to the impedance matrix and what happens to the sequence impedance matrix of this kind of transmission line when it is fully transposed. Now to do that, we have already derived that we have that for a transmission line we have this equation that we have. So we are just simply writing this. These we have already derived, so then therefore we are not really, again we are just simply recollecting them. We are just simply recollecting them, and then ZS is essentially the Basically the impedance of the line per unit length, S is the total length as we have already indicated, and where of course we said that Z11 is equal to Z22 is equal to Z33, sorry, this is 1 2 3, this is 1 2 3, this is the position, these are the position, but the position. Position, right. So these are the positions. So we said that Z11 is equal to Z22 is equal to Z33 is equal to Zs, and we said that Zk1, that is the definition, is S1 Z12 plus S2 Z23 plus S3 Z31, that we have said. Then Zk2 is equal to S1 Z13 plus S2 Z21 plus S3 Z32, and Zk3 is S1 Z23 plus S2 Z31 plus S3 Z1 2. So these definitions we have already defined. So then therefore we are just recollecting them, and of course here we also need to remind ourselves that Z12 is equal to Z21, because this matrix, because these impedances are symmetrical, and then Z23 is equal to Z32. These also we need to remind ourselves, and Z31 is equal to Z13. Now what was the expressions of, let's say, all these Z11 and Z21, and just simply for simple recollection we have already done it, that Zij is equal to Ra plus Rd into plus j omega k log dE by ds. This is omega per mile, omega per unit length, I would say unit length, and this is for I is equal to j, and that is equal to Rd plus j omega k log dE by dij omega per unit length, and this is I not equal to j, and I and j they vary from, and I j they vary from 1 to 3. So these are the definitions. So with this we can calculate everything. Now let us see that what happens when S1 is equal to S2 is equal to S3 is equal to 1 by S. So now when that happens, so then therefore what happens to Zk1? So then therefore if I use these relations, and if I use these relations, so then therefore I can say that now for a fully, now for S1 is equal to S2 is equal to S3 is equal to 1 by 3S, I can say that Zk1 is equal to Zk2 is equal to Zk3 is equal to S by 3 Z12 plus Z21 plus, sorry, Z23 plus Z31. That is obvious. Let's say that this is denoted as Zk. Now, these relation we get by applying these relations here and also utilizing these expressions. So, then therefore, then my equation becomes that delta V A summation V V is equal to S Z S Z K Z K Z K Z K Z K. Right. So, then therefore, I can from this relation I can simply say that ZABC is equal to nothing but is ZS, then ZK, 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 ZS, ZK, ZK. So, then after that, so with this ZABC, if I apply now, so then from this ZABC I can calculate Z012. I will write that please verify. So, Z012 by applying the formula that A into Z ABC into A inverse, if I apply that formula and then if I calculate Z 012, it will turn out to be ZSS plus 2ZK and 0 0 0 SZS minus ZK 0 0 0 SZS minus ZK. I would write it that I am not really deriving it, I would say that please verify it. Right, you can always verify it. So, now let us see now what is Z0 then. So, then therefore, from here I can say that Z0 is equal to SZS plus 2ZK and Z1 is equal to Z2 is equal to SZS minus ZK. So, again we have already seen and that fact is again being re-established that the positive sequence and the negative sequence impedances are same and the zero sequence impedance is greater than the positive sequence and the zero sequence impedance. Now, let us see that what is the value of Z0. Now, we will utilize the expression of Zs and Zk and then now what is Zk? Now, what is Zk? What is Zk? Zk would be 1 by 3 Z12 plus Z23 plus Z31. So, 1 by 3. What is Z12? Z12 is Rd plus j omega k log, so it is Rd plus j omega k log d by d12 dE by d12. Then Z23 is Rd plus j omega k log d by d23, and Z3 is Rd plus j omega k log d by d31. Just simply substituting the expression of Z12, Z23 and Z31, right? So then therefore I can say that it is 1 by 3 into 3 Rd 1 by 3 into, what is actually S by 3, sorry, it is S by 3, S by 3, S by 3, sorry, S by 3, 3 Rd plus j omega k. If I take common, then it becomes log dE by d12 plus log dE by d23 plus log dE by d31. So then therefore so it is S by 3 into 3 Rd. So basically it will be S into Rd. So I can say that S into Rd, I take S common, then Rd I take inside, and then 1 by 3 I take inside, and the j omega k and log dE cube by d12 d23 d31. Right. So then therefore if I now utilize the logarithm rule, so it becomes S into Rd plus j omega k log dE cube by d12 d23 d31 whole of 1 by 3. So that means S into Rd plus j omega k log dE by d12 right. Now let us define, so then we write it more in a second form as S into Rd plus j omega k log dE by dEq, where dEq is equal to d12 d23 d31 cube root of product of d12 d23 and d31. So this is the expression of zk. Now with this expression of zk, we will now evaluate we will now evaluate z0. So, hence z0 is s zs plus 2 zk. That is the expression of z0, that is what we have said, that is zs into zk. And the expression of zs is basically Ra plus Rd plus j omega k into log d by ds. So, then therefore, it would be, so if I take s common, if I take s common, so it is Ra plus Rd plus j omega k log dE by ds. So, this is the expression of Zs, you see this is the expression of Zs, and then 2zk, we got this expression of zk from here. So, it would be 2rd and we have taken s common. So, 2rd plus 2j omega k, or rather j 2 omega k plus j 2 omega k log d by dq. Right. So, that is what we will get. So, if I do this calculation, so s into Ra, sorry, s into Ra plus 3rd plus j omega k log dE by ds plus j omega k, 2 I will take there. So, log dE square by dEq square. Right now, if I do take common j omega k and j omega k common, so s into Ra plus 3Rt plus j omega k. If I now here apply the logarithmic rule by taking j omega k common, so it would be log dE by ds plus log d square by dEq square. So, it would be s into Ra plus 3Rt plus j omega k log dE cube, these two will be multiplied by ds into dEq square. Right. So, this is the expression of z0. So, this expression is in terms of the resistances of all the wires, as well as the ground resistance, as well as the dimension of the wires. Now, let us look at the expression of Z1 and Z2. Z1 is equal to Z2. So, that is SZS minus ZK. That is the expression SZS minus ZK. So, this is the Zs. So, S into Ra plus Rd. So, this is S into Ra plus Rd plus j omega k log dE by ds. So, this is Zs. So, this is the expression of Zs. This is the expression of zs minus zk. The expression of zk is s into rd plus j omega k into log d by dq. So this is rd. So this is minus rd minus j omega k log d by dq. Right. So then therefore I can write it down as rd cancel out, ra plus j omega k then log d by ds minus log d by dq. Right. So it would be s into ra plus j omega k log d ds into d by d cancels out. In other words, s into ra plus j omega k log deq by ds. So this is the expression of z1 and z2. So we can see, so essentially, and we have already proved that z0, and of course from here also we can say that z0 is greater than z1 is equal to z2. And here also, from here also I can say that the further I can also say that for a fully transposed line, so for a fully transposed line I can say that the sequence impedances are, I can also say that sequence impedances are completely decoupled. So sequence networks, I should say that sequence networks. So okay, before that I should write down, let me write down. Now from this network I can, now from this I can also write down that also I can write down that V0, V1, V2 is equal to say Z0, 0, 0, 0, Z1, 0, 0, 0, Z2, I0, I1, I2, where of course Z0 is just now said that is Zs plus 2Zk, and Z1 is equal to Z2 is equal to Zs minus Zk. So from here I can say that V0 is equal to Z0, I0, V1 is equal to Z1, I1, V2 is equal to Z2, I2. So, or in other words, that sequence networks, I can say networks, that is, or sequence networks are can say that sequence networks are completely right. So that's what we have proved. So with this we now end this lecture, and then in the next lecture we will be looking at one example. Thank you.